Hello everybody, and welcome to our first video for AP Physics 1. Just to draw your attention to a couple things in the notes so you know what we are doing. First of all, right here it says what unit this is. So this is Unit 1 Kinematics. This is the first lesson that we're having in the video. These are some of the concepts that we will cover in this. The main section here where it says notes and examples, the main section of the notes is where we will write down most of our information. But in the margins, I'm going to have some concepts delineated in the margins, so kind of break them up so you know what each thing is about. In addition, I will use the margins from time to time to do like random notes, but I also encourage you to write down questions. So as you're watching, if questions come to mind, write those questions down. That way when you get back to class, then you can ask those questions, we can talk about them, we go over them, and you won't forget them. Because I know that for a lot of people, that's one thing that they don't like about videos for notes is they can't ask anyone a question. You can still ask me questions. Ask me lots of questions. Well, I suggest that you write them down. Okay, let's go ahead and get started. So one thing we need to talk about is the difference between scalar and vector. And this is a concept that some of you have learned in your math classes, some of you have not. So let me just really quickly point out the differences. A scalar quantity is just a number, just a random number, not a random. It is a number, it has units, and it's describing the size or the magnitude of something. For instance, 5 meters per second, 250 meters. 7 seconds. Those are scalars. A vector has units and direction, and that's the difference. Scalar does not have direction, vector does. So instead of just saying 5 meters per second, we say 5 meters per second or 25 meters per second to the north, what direction it's going. The displacement, how far it went, 12 meters, but also the direction to the south. So that's the difference between vector and scalar, and that becomes very important in this unit so that we know to know the difference between them, because there are some different concepts we have to focus on, vector versus scalar. Okay, so this next section I go through several different examples. So volume, does it have a direction? No. If it does not have a direction, it is a scalar. Now these next two, they have direction. And so if they have direction, they are vectors. You probably have not seen this N before. That N stands for newtons, and newtons is a measure of force. And we'll get that more next unit. This time, velocity, 15 meters per second. I think that's supposed to be 25 degrees north of east, and it's a misprint. So that right there, I think it's supposed to be 25 degrees, not 25.0. So 25 degrees north of east, it has a direction. If it has a direction, it is a vector. Now this next one, same number, but does not have a direction. Therefore, it is scalar. And I wrote velocity on there, and that really should be speed. So the difference, a lot of times, the quantity might have a different name if it's a vector than it does if it's a scalar. Sometimes they're the same, but a lot of times they'll be different. So for instance, if it has a direction, it's a vector, it's called velocity. If it does not have a direction, it's a scalar, it's just called speed. Similar with distance. So this does not have a direction, so it's a scalar, it's called distance. This one does have a direction, and so it's a vector, and so we call it displacement. So sometimes there will be different names depending on whether or not it is a scalar or a vector. Okay, concept 2, displacement and distance. We were just talking about that. What's the difference? Well, distance is a scalar quantity that has a base unit of meters in the SI system. Displacement is a vector quantity whose magnitude is distance. What do I mean by magnitude? Well, magnitude just means the size, how much. So back to our up here we had some examples. 9.29 is the magnitude, but the negative x direction is the direction. So a vector has magnitude and direction, a scalar just has magnitude. Now something that is a little bit confusing, I think, can be if you don't know the difference. In physics we often use x for distance. So just be aware, because sometimes people want to say x is on the x-axis, but often distance is on the y-axis. Anyway, x typically will stand for distance. That delta means change in. So again, some of you have learned this in your math classes, some of you have not, but that little triangle means delta, and the delta means change in. So delta x is the final minus the initial of whatever distance you have. Okay, so here's an example. Will you stick in the word 1 meter? Okay, a ball is thrown 1 meter straight upward and comes back down to where it started. What is the total distance that it has traveled? Well, the distance is 2 meters because it went 1 meter up and 1 meter down. Next question is, what is the magnitude of the net displacement? By net displacement, what we do is we calculate that. This is like delta x, that's the net displacement, by the final minus the initial. Well, it started down here at the bottom, we'll say at 0 meters high. It went up and then it came down and it landed, sorry, that should be my final, it landed also there. So it landed at 0 meters, it started at 0 meters, so my total displacement is 0 meters. Okay, that was displacement and distance. Let's talk about speed and velocity. So speed, which is typically described as average speed, is a scalar quantity that has base units of meters per second in the SI system. So we talk about average speed. We've talked about this already when we were talking about our buggies. The speed is the distance divided by time. Now, this only gives the average speed, which really is not very helpful. And so we are rarely going to use this. Now, I do think that it's important enough that you might, for instance, write it down on your formula sheet. Because it is something that we use, but you really have to use it sparingly because we have other better equations to use. But use this one sparingly and only when you have an average speed. Okay, velocity, however, is a vector whose magnitude is speed, and we find it through this very, very similar, right? These two equations, very similar equations. The only difference being we have a change in x and a change in t. You will want to memorize these because we do have those equations on our equation sheets. This one actually is not on our equation sheet. Okay, so far, we're going to turn the page here in just a second, but so far, if you have questions, make sure you write your questions down and bring them to class. Let's go ahead and turn the page. A minute ago, we were talking about average speed. Now we're going to talk about instantaneous velocity. The instantaneous velocity is the velocity of an object at a specific instant in time. Now, I have this limit here. Let me tell you, you don't really need to know this. If you're a calculus person, this might make sense to you. It should make sense to you. But for this class, we don't need calculus, so we're going to ignore that for now. Instead, take a second to draw this diagram. You might need to pause the video. Draw this diagram or one like it. Let's say we have position on the y-axis, time on the x-axis. We have plotted this red line, and might have been like a scatter plot of the velocity. Once we plotted that, we then created a line of best fit, which was our average velocity. Okay, average velocity we've talked about is kind of helpful, but not super helpful. Instantaneous velocity is what happened exactly at that spot. And for that, we find the slope of the line tangent to that curve. And again, a little bit of a calculus concept. We don't need to worry too much about it, but I think sometimes it helps to see it graphically. And so this is my answer to number 5. Is it possible to have an average speed below the speed limit, but still get a speeding ticket? Yes, of course, that happens all the time because the speeding ticket is instantaneous velocity, whereas average velocity is the whole range of time. So if you think about that, if you get pulled over and you say, but back there I wasn't speeding, and so my average is lower. They don't care. They're talking about at that instant, at no point during your driving are you supposed to be speeding. Hope that helps you think about how to distinguish between instantaneous velocity, which is very important, and average velocity, which really isn't all that important. Now, when we talk about velocity, we also then have to start talking about acceleration. So acceleration is a vector quantity that has base units of meters per second, or meters per second, or meters per second squared in the SI system. And the way we find acceleration is by this. And once again, you ought to memorize this, and you probably ought to go ahead and write it on your formula sheet so you have it. It is not given to you because I think AP thinks this is so basic you ought to know it on your own. Memorize this. Notice the units indicate that the acceleration is time rate of change of the velocity. In other words, if we think about the numerator, we have velocity, which is meter per second. Denominator is time, which is seconds. So that's meters per second per second. That means how fast are you increasing your speed. So you're speeding up. and that is measured in meters per second, or it's also called meters per second squared. Okay, so for example, if a vehicle has a velocity of negative 20 meters per second and stops in 4 seconds, what is the average acceleration for the vehicle? These subscripts, little f means final, and little o, oftentimes that's called ought. Sometimes I just use an I because it really means initial, but a lot of times physicists will use ought. So that's VF minus V ought, TF minus T ought. I typically will just say initial. So final velocity minus initial, final time minus initial time. So the final velocity, well, it stops, so it must have stopped at 0, because that's stopping, 0. And then its initial velocity, though, was 20.0 meters per second. And then it stops in 4 seconds. So the final time on the timer, when you clicked the timer, it was 4 seconds, and the initial time started at 0 seconds. Okay, so we have a negative, that's a positive 20 meters per second, and a 4 seconds on the bottom, that's 5 meters per second squared. Or in other words, every second it is slowing down at 5 meters per second. Every second it changes another 5 meters per second. So we do need to talk about the signs, and does that mean it's speeding up? Does that mean it's slowing down? We're actually going to spend quite a bit of time talking about speeding up and slowing down. When we say negative 20 meters per second, that means it is moving to the left. So the speed is 20 meters per second, but it's going to the left, and since it's going to the left, we're saying negative. The positive 5 meters, that should be meters per second squared, that means that the acceleration is to the right. Okay, so graphically, if we think about this graphically, you are moving to the left at negative 20 meters per second, or negative 20 meters per second squared. There's some acceleration going on. And again, we'll get into this more next unit, but acceleration means something has to be pushing it. So something is pushing against it with an acceleration of 5 meters per second squared. In other words, every second, it's losing 5 meters per second. So it starts out at negative 20, but then it's going to negative 15 and negative 10 and so forth and so on. And so what's happening is it is slowing down, and it's going to take 4 seconds. If it's going at 5 meters per second, then that's going to take 4 of those, so 4 seconds for it to reach the stopping point at 0. Okay, this next part we will go over quite a bit in class, but if a velocity and acceleration have opposite signs or opposite directions, then the object is slowing down. But if velocity and acceleration have the same sign or the same direction, then the object is speeding up. So let's think back to our arrow a minute ago. So if this is our 20 meters per second, if the acceleration was pushing it this way, it's like you've got something pushing it, like the wind is pushing you, making you go faster. So now you're going to be accelerating. But in our case, you're going against the wind, and that's going to slow you down. So opposite signs, slowing down, same sign, speeding up. The last thing on this page is a little bit of sentences here, and then another limit. I will just point out that you don't need calculus for this class, but you do need calculus if you are intending to take the AP Physics Mechanics C test. Some people choose to take that test rather than the AP Physics 1 test. And if you're in calculus, you can do that. Also, if you're in calculus, you just understand this kind of thing a little bit more. We don't need that for this class. I've had lots of people in this class take the AP Physics 1 test while taking a Honors Algebra 2, and they did just fine. So you don't have to have calculus. Don't worry about that. What I do want you to worry about is, what questions do you have? Write some questions down in the margin so when we come to class next time, you can ask and I can help you with those. So that's the end of our first video. We'll talk about it more when we get to class.